Hi friends, I am Pritesh Pawar from Walchand College of Engineering, Sangli and Electronics Engineering Student Association, ELISA, one of the best club of the WC Sangli. Today we are going to take a tutorial series on Digital Electronics 15. In that topic we all study a special type of the counter, that is ring counter, and also the Johnson counter. Then what will we study? Ring counter, its circuit diagram, protest simulation, state diagram, waveform and application of ring counter. After that, Johnson's counter. In that, the same circuit diagram, protest simulation, state diagram, waveform and application of the Johnson's counter. Ring counter. Then what does actually ring counter mean? Ring counter is a shift register counter in which the output of the last flip-flop is connected to the first flip-flop. We can see here in the diagram that output of the last flip-flop, that is the D flip-flop, is connected to the input of the first flip-flop, and here is the common clock connected to the all flip-flops, and it is a positive edge triggered clock. And here is the clear circuit that will clear or the reset the whole flip-flop or the whole counter to the 000, because the only change in the shift register and ring counter is that the output of the last flip-flop is connected to the input of the first flip-flop or the shift registers. Now we will discuss in the protest simulation what is the common clock. In that, the preset when equal to 0 then q equal to 1, and when clear equal to 0 then q means the output of that flip-flop is equal to the 0. When the preset is the active low, then it sets the output of the flip-flop to the high, and when it is high then output of the flip-flop becomes 0. When the clock is given as the negative edge triggered, then the change will make in the at the falling edge time, and when the clock is given as the positive edge triggered, then it makes the change in the rising edge. Now after that we will discuss about the protest simulation, and here it is our protest simulation. Okay, I will run it now. It is not initialized, so we have to initialize the first ring counter. And here is the ring counter. The counter is moving 1000100. Here when now we see that the output of the last flip-flop is connected to the first one. Falling at the rising edge, here we have connected the positive edge triggered clock, so at the rising edge of the clock, then the output of the last flip-flop will then the flip-flop will changes its output, and to reset the circuit we will use the clear circuit, and here it is. If I press the push button, that is here, then it will reset the whole counter to the 000, and to initialize it again we will press again this push button. And this is all about the simulation. Now we will stop it. After that, again our PPTs. Okay, and here is the state table. Here we see that there is only the 4 states of the ring counter, because we have connected only the 4 flip-flops here, so the ring counter gives only the same number of the states that is equal to the number of flip-flops of the ring counter. The first state is the 1000, after that 0100, then 0010 and 0001. Hmm. In the timing diagram of the ring counter, we see that at the rising edge, at the rising edge, we can see that at the rising edge there is a change in the clock, so it will make changes in the shift register output, that is the QA, QB, QC and QD. Now let's move to the advantages of the ring counter. Ring counter can be implemented using the D flip-flop and the JK flip-flop. It is the self-decoding circuit. Here is the main advantage of the ring flip-flop. In the other counters, means the binary counter or the normal counter, we have to decode the signal, or we have to decode the output of the counter. But in case of this, we do not need to decode the output. But we get only the n number of states for the n flip-flops. That is, we get only the 4 states for the 4 flip-flops. So in case of the binary counter, we will get 2 raised to n, means 2 raised to 4 number of states for the 4 flip-flops, and these are the 16s. But in case of the ring counter, it is only the 4 steps. So this is the disadvantage. And also we need to initialize the counter at the first, that is, we have to start the counter with the 1000. Let's move application. It can be used where we need the sequential controls. It can be used in the divider circuits, and ring counters used to count the data in the continuous loop. So these are also helpful. After that, Johnson's counter or the twisted ring counter. Why there is need of the Johnson counter? First of all, the question is why there is need. Because need to initialize the counter of the ring counter is not in the same as the Johnson's counter. So here there is no need to initialize the counter. After that, the number of states is equal to the 2 into the number of flip-flops. Hence, we get the 2n states for the n number of flip-flops, and these states are double than the ring counter. In ring counter, we get only the n states for the n flip-flops. After that, there is the circuit diagram. Here we see that the output of the last flip-flop, that is the Q bar output, not Q output. Q bar output is connected to the first input of the D flip-flop, and move towards, here is the Q bar output of the last flip-flop is connected to the input of the first flip-flop. Sorry, it's ring counter. And here is the Johnson's counter. I will simulate the simulation, and it directly starts, means it no need to initialize the counter. So here it is, and here the Q bar output of the last flip-flop, that is connected to the input of the first flip-flop, and the clock is the positive edge triggered clock, so it will make the changes in the counter at the rising edge of the clock. And the reset circuitry is connected to the R, is the reset, and here yes means the preset circuit. The reset will set the circuit of reset will set the output of this flip-flop to the 0. If I press this push button, then the counter is initialized again. And here it is all about Johnson's counter. Now the state diagram. Here we see that the truth table is initialized from 0000. Then there are, we see the 8 number of different states in this counter, because we have used the 4 D flip-flops here, and this will the reset circuitry, and the reset circuitry will set it to the 0000. After that it moves to the 0001, then 0011, and this will continue till it get again to the 0000. This is the timing diagram of the Johnson's counter. Here it will make the changes in the flip-flop at the rising edge because we have connected the positive edge triggered clock. And there are the 8 different number of the different states. Here these are those 8 states. We can see here that now we have seen the advantages of the Johnson's counter over the ring counter. After that, disadvantages. Only the 2n number of the states which are very less than the binary counter. In the binary counter for 4 flip-flops, it will give the 2 raised to n different number of states. Means it will give the 16 different number of states. But in this case, it gives only 2n number of the states. And if the Johnson's counter is in its missing state, then it requires the number of clock cycles to go in the present state. Means if it is in the state like the 0 0 1 0 0, then this state is not present in the whole truth table. So in such a case, it needs too many cycles for initialize it. Okay, applications. It is used in the stepper motor control. It is used in the divide the clock inputs by varying their feedback loops. It can be used in a three-stage Johnson ring counter could be used as a three-phase 120-degree phase shift square wave generator. And the difference between them is the most number of states, that is here only the n number of states, here the 2n number of the states for the n number of flip-flops. Ring counter is need to initialize the first, and Johnson's counter is no need to initialize the counter. And here is from my side. I think the video will support you to study more, and if you have suggestions, please visit us or like us on the Facebook. Thank you.